Hello everyone, thank you for coming. Welcome to almost summer season for the ICARL seminars. Welcome for those of you that is the first time here. This is a series of talks about autonomous agents, originally reinforcement learning. We're moving a little bit beyond that, but still that is very close to our heart. I guess also for our speakers today as well. But we have very interesting things to talk about today that are going beyond that. So our speaker today is Jake Bruce, research scientist at DeepMind. He did his PhD in Australia. I don't remember the uni.
Neither do I.
Wow, come on.
Queensland University of Technology.
Queensland University of Technology. It's a good one. You're here today. So. Then you were working on robotics, if I remember correctly. And then he has working very interesting stuff also for the topics of this seminar, such as the NetHack project. If you don't know that, there is a very nice talk from 1.5 years from Tim Rockwell talking about this environment, about you work also on Gato, remember you said. This agent that was able to play many games, move robotics, and talk at the same time all together. But today we're talking about something different, something more game-oriented. I'm not going to enter more into that. You probably have seen that on the media. You wouldn't be here otherwise. But before jumping into that, these seminars are thanks to our sponsors, InstaDeep and DeepMind. Thanks to them also, we have some food afterwards where we will be networking. You will have a chance to talk more to Jake. And also, if you're interested in all this stuff, we have a reading group happening when the seminars are not going on. And it's about, we gathering together, reviewing papers like the one that Jake is going to present today, and try to go a bit more in depth. With all that being said, Jake, the stage is yours.
Great, thanks. Thanks everyone for coming. So I'm Jake. I'm going to talk about generative interactive environments, or as we call it at DeepMind, Genie. So this is work with a bunch of my great colleagues at DeepMind, and so let me motivate it a little bit. So if you think about what it takes to succeed at a deep learning task, so either you got to have a bunch of labeled data, as in the supervised learning case, or you got to have a really good simulator. So once you have access to a good simulator, this reliably leads to like superhuman performance. So we see that in Atari, we saw that in Go. But what's the simulator for AGI? And this is not clear. You kind of have to simulate everything. But it's clear at least that the more you simulate, the better. So basically, all you need is data. In the RL case or the agent case, all you need is experience, and ideally kind of online exploratory experience. So how can we actually scale to the kind of tasks that we talk about when we say AGI or ASI, beyond human capability? So at the very least, we have a bunch of environments that we can use already. So simulated robot environments, video games, specific RL benchmark tasks, many, many other things that we could train on. So that's what we did in Gato. We generated a whole bunch of expert, specialist agent data, and then trained on all of that in a behavior cloning fashion to distill into one big transformer that can perform all these different tasks to a very high level of capability. So it's clear that you can kind of achieve this kind of distillation into one model that is then general across these environments. Another approach is to imagine the kinds of tasks that you want your agent to be able to do, and then build a simulator that can kind of simulate all of them. So engineer a very complex environment that represents all the kinds of interactions that you want your agent to know about. This is what some of our colleagues did in XLand. Very thorough kind of like combinatorial specification of all these different tasks that you can do in this particular environment. So it's limited to this, what's called XLand environment, 3D environment where you can move around and interact with other agents. But still, it's kind of limited in the sense that it's just this one very complex environment. A video. So this is what happens when this agent performs in the environment. So it's kind of rapidly, it's trained in kind of RL squared fashion. So it's kind of meta learning via seeing multiple episodes in a row. And what happens is the agent gets multiple trials and can move around and explore and observe what it gets rewarded for. And then in any given episode, it has time to kind of adapt to what the task is for that episode. In the paper, you can see like this is achieving approximately like the level of how fast humans can adapt on this particular environment. Let's see. Okay. Yes. So, meantime. So it is very impressive progress. That said, like there's definitely more to go. When we talk about AGI, we're talking very, very broad. And so the question is, what's actually going to scale to that, the difficulty of that kind of task? So I think the basic takeaway here is that manually designing things introduces a very narrow bottleneck into how many different environments we can produce. So whether you're manually onboarding things that other people have already designed, manually designing your own simulations, or collecting data, which is also very expensive, we want these things to scale in a way that's uncoupled with human labor, coupled with something else. And the bitter lesson suggests that that something else is compute and search. So basically, generative AI is all over the place right now. We're getting to the point where we can easily generate videos, and the only thing that differentiates a video from an environment, which is what we want for AGI, is control, right? So you at least a visual environment, let's say, for the intents of this talk, like talking about visual environments like video games. So if you can inject control into video that you're generating frame by frame, then you've got kind of a world simulator that is worthy of the term. So I think that it's very clear that you can in principle do something like this. So how do you do this? You just need the data. And in our case, we use internet video. And we consider this a foundation world model. So it's not just a video model, it's a world model because we have control. So, or rather, I should say, it's not just a video model because we have control, and it's not just a world model because we learn it from unlabeled data. So just passive kind of video data that's available in the wild. So this is how it works. So we have this model, which we call Genie, and the idea is that given an image, you can learn the set of possible outcomes from a transition in this environment, unsupervised, and produce the next output in that video stream. And that effectively is an environment. It's a video game, it's a foundation world model. And so now going into specifics about how this model actually works, like from the paper, in this case we're using a technique called masked Git. It's a iterative, generative model where you kind of learn to unmask the tokens that are in your input stream. And as you unmask more and more from zero, you end up with a complete image. So the three components that this requires in our setup are a tokenizer. So these are transformers, so we want to be able to turn videos into tokens. A dynamics model that can predict what the next frame is, given some tokens and, crucially, an action. And then the question is, how do you get the actions? Because this, remember, is passive video data, completely unlabeled. We have what we call a latent action model, which effectively learns how to kind of compress the future into a very heavily bottlenecked latent representation. So the video tokenizer, this is the thing that you'll be familiar with if you operate in the kind of transformer cross-vision spaces. So given a set of input images, aka a video, you want to apply some encoder to it and get a discrete set of representations such that you can then decode them back into a reasonable facsimile of the input video. And it's from that reduced space, the token space, that's where we operate our control. But then, taking videos in and producing videos out for humans or agents is handled by the encoder and decoder. So these are, this is a standard kind of setup, VQVA. The distinction in our setup is we use a spatiotemporal transformer, which is like a little bit of extra juice on top of a standard VQVA as if it was just a normal kind of video autoencoder. The real secret sauce, I think, is the latent action model. So after all, we're a video model, but we want to be controllable, so we need actions. So what is that actually? It's a very heavily compressed bottleneck over the future. And what does that mean in this case? So we encode, similar to the tokenizer, we'll encode a video into a set of discrete latent actions. So these are like, they take one of 8 different values, right? So very heavily bottlenecked in between each frame. And the objective of this model is to be able to predict what the next frame is given the decoder. So very simple kind of self-supervised learning problem. Just given the input video and a set of latent actions that that spans the gaps between those frames, learn to predict those next frames given only the previous context, because it's like, it's causal like transform. And it turns out that these basically turn into like pretty good controllable latent variables, and I'll show you what they actually look like later. And then how to actually generate the tokens of the next frame. This is the mask-it that I referred to earlier. So given the tokens of the previous frames, the actions that you've learned to stitch those frames together into dynamics, you can mask these tokens at training time, and then with a random fraction, between 0 and 1, and then your dynamics model is learning to predict the missing ones. And if you have a model that can predict the missing tokens for any possible mask, then at inference time, you can, I got a slide on inference time in a second, but you can start from 0 and slowly fill it into inference time. And so this is the ST transformer I was talking about, spatiotemporal. This slide is probably a little arcane, but effectively what we do is we interleave a layer of temporal attention with a layer of spatial attention. So what that looks like in code is like you fold the batch dimension in with the time, and then you fold the batch dimension in with the spatial image dimensions, such that you are doing your attention over either the time dimension or the spatial dimension, followed by a feed-forward layer. You compose those in a nested way, just like a normal transformer, and that allows the model to very efficiently attend to time and space. We're not the first to do this, but it's coming up a lot in the literature. It's a really useful tool. The reason why you'd want to do this is because if you had flat, and we did try this early on, completely flat token streams, like you would with GPT or whatever, that's the quadratic attention cost for having those all attend to all the others just limits your scaling. So this way, it's still quadratic in time, but the time dimension is a lot shorter because for each image you have it like as a different dimension. You might have 16 frames in your video, then your temporal attention is over 16 frames rather than every single token. And then at inference time, that's what I was referencing, we have this iterative generation process. In practice, it takes about 25 model calls, and the idea is you start with only your context, so the frames you've seen up until now, and then you present the model with a completely empty image, so all tokens masked. You predict a few of them, you actually predict all of them, but then you take the ones that you're most confident about. Keep iterating this, similar to like the wave function collapse algorithm, if you're familiar with that from game development. And then you end up basically filling out the whole thing, starting with the most the things you're most certain about and kind of spreading those outward. And that allows for a really efficient form of inference, more efficient than vanilla distillation, vanilla diffusion, or iteratively actually predicting every single token in raster order, right? That would be, in our case, like 1,000 tokens. Here we can get away with 25 function calls. And remember, the goal of this thing is to be an environment. So like ultimately it has to run at frame rate, which we're not quite at yet, but you need to worry about step time. So that's why we do this kind of technique. Okay. Yes. Yes.
With this technique, imagine like hallucinations and like jumps, and you have like a duck, and then a duck disappears and comes back a few frames later. Like, what sort of like ideas do you have to prevent hallucinations, to prevent like patchy and not smooth video streams that you predict?
Yeah, so in practice, we don't tend to see that problem too often. So basically, the likelihood of we're decoding one frame at a time. So you'll go from a completely empty frame to a completely decoded frame before you ever start the next one. So the likelihood of observing like inconsistent dynamics there is basically a function of how good your model is. So if the model is not good enough, then you might observe weird dynamics like that. But we found that like our biggest models are about 10 billion at the moment. We found that at that scale, we don't tend to observe these problems. And in fact, even at small scale, the problems we tend to observe are not really of that form. They tend to be more like if you have your kid, so I haven't even showed the data yet, but like imagine like playing Super Mario or some kind of like 2D game. If you like walk to the right for a whole bunch of frames, you would imagine that it generates more content than was present in the initial frame. In practice, with small models, we tend to find that that content is very boring. So it's like streaks the content across the screen rather than generating interesting platforms and things. So I'd say, yeah, in essence, like that's not the kind of problem we tend to see. But the hallucinations we do tend to see are more like mode collapse of like really boring generations. If that makes sense.
It's mostly because you're training on like game data rather than like real world data, which is maybe more complex. It's like the occasional bird flying or whatever.
Yeah. I mean, so I think I have some slides about this. But when the data set you train on is very chaotic with a lot of like unpredictable behavior, you get noticeably worse performance. And certainly sometimes that takes the form of like pretty chaotic performance. Okay, yeah. So this is actually what the outputs look like. So like here, it's very low resolution, just due to limits on scaling. But effectively, what we do here is we prompt a text-to-image model, like Midjourney or Google Imagen, and we ask it to generate a particular frame, and then we give that frame to our model to actually animate it and control it. So the latent actions that the user chooses while playing the game determine, like, oh, this guy is going to jump to the right and up, and you'll see that there's a little bit of kind of like animation of his sprite, even though none of that is present as like privileged information, right? It's just a bunch of pixels. But the model in practice kind of zooms in on like the particular thing that looks like it would move in a game if this was a game, and tends to be able to animate it relatively well. Since these results are from like October, since then we found that further scaling and improvements can lead to much better video quality as well. But I don't have those ready yet. But you can also generate very diverse frames, so diverse trajectories. So here is another kind of text-to-image generated initial frame, and we'll see 4 different trajectories. And here, I think actually it's a pretty good demonstration of what I was saying earlier to your question. Like you can see that this guy here. So like you'll see when it goes off the screen, it tends to generate kind of repetitive, simplistic textures that nonetheless are kind of fitting the distribution relatively well, but maybe mode collapsing a little bit relative to what you could imagine seeing in an image like this. So those are weaknesses that we've seen empirically kind of improve with scale and other improvements to the model. But the point is you can generate different trajectories, which is ultimately what you want from a controllable environment. These work for non-text-to-image screenshots. So here we have a cartoon kind of drawn by one of our teammates, and you can kind of control it a little bit, move the character around, climb the ladder. Here we have an image drawn by the daughter of one of our son of one of our advisors, and you can see that it's kind of animating the picture across the screen. Then we have another hand-drawn image where the character is clearly kind of simulating some kind of jump behavior, and you can also observe a bit of parallax here where the platforms in the front are moving at a rate faster than the background. So this is all learned just purely end-to-end from the videos that we train on. And some real-world images. So we have a dog, this figurine of Thor, and a pizza, and you can see it kind of is able to reasonably well cope with like all of these signs of life at least, although you might want improved quality, and that's what we're working on now. So basically, the question you might have is like, why on earth would these latent actions mean the same thing in every different state, right? They're just compressions over the future, and it's not obvious that the jump to the right action in a Super Mario video should be the same latent variable as the jump to the right action in a completely different environment that has nothing in common visually. But in practice, we find that this tends to actually happen. So unfortunately, the bottom right one here is a little out of sync with the other three, but basically this is the same latent action played on all four environments, and the same sequence rather, and you can see that a similar kind of trajectory is happening in each one, right? Move to the right, move to the left, jump up, and as I mentioned, the one on the bottom right is just, I think we have the frame rate wrong or something, but it's the same latent action sequence, and you can see kind of a left, right, and a jump up. So this is a mystery to me, why this would happen. I think that in any reasonable universe, you would expect that it would be hard to have these kinds of things emerge. But for whatever reason, so far, these have been remarkably consistent. Yeah.
So, like, a very few number of latent variables, right? Like, if you were to increase the number of latent variables, you'd probably see like more randomness.
I imagine you would. So we have 8. It's a discrete latent variable with 8 possible values. So it's extremely think about it like a very old retro controller, extremely low dimensional control. And you're right, I think that very heavy bottlenecking probably gives you a lot of this. I'm still a bit surprised, but as we move to higher dimensional and maybe non-discrete control schemes, this might be a real problem that we have to deal with.
Have you since scaled it since October and seen any results?
So in terms of scaling the action space, we've gone as high as 20. It does get pretty difficult to control it as a human when you go too many. So in practice, the user interface is you upload an image or a video, and then it will give you, show you visually all the outputs. And of course, if you get 10, it starts to get pretty unwieldy. But it does work, and in fact, under the metrics in terms of FVD or whatever, the quality seems to improve the higher action, the action count. Up to the limit that you just I expect the consistency, or at least the semantic interpretability of each of these actions might suffer.
How do you get over the problem with scaling essentially the ground truth data you have? Because now you're essentially mapping to a couple of actions, which is easy to annotate. How can you actually map out to a larger actual vectors to input?
Yeah, so we don't have any action labels. So this is all completely unsupervised. So we just have a VQ vector quantization bottleneck at the middle of the model there. Go back to it. And so no action labels here at all. Instead, this latent vector A here is completely learned unsupervised. So that's the nice thing about our approach. Basically, scaling is our number one concern. We want to be able to scale only with the quantity of data and not in any way with the quantity of human labels. So effectively, the data here being just videos. Just give me all the videos on the internet, and I can apply this technique to it with zero human effort, which is the hope. In practice, we find that, like I mentioned earlier, a bit of data set curation is valuable. So that's you want high quality videos. You don't need to do
what would be required to extend it to a 3-dimensional game instead of just a platformer?
Yeah, so I have some initial kind of results there in terms of robotics, which is not a game, but it kind of works. It works pretty well, actually. So I'm not sure where that is in the deck, but we'll get there. The short answer is that ultimately the model is as good as your data is, and it works very well in 3-dimensional environments, but it's the action space is limited. So for consider an Xbox game, right? You have at least maybe 4 continuous axes plus a bunch of discrete buttons. It's not obvious to me how you could capture all that control with only 8 latent variables, for example, that discrete latent variable with 8 categories. But there's nothing. The only reason we choose this very narrow 8-way bottleneck is for simplicity of playing with the model. If you had an actual Xbox controller as an action space, you would get much better metrics because that's a much more expressive compression of the future. But it'd be hard to evaluate it, it'd be hard to probe it, and it'd be hard to interact with it, except with an Xbox controller, right? But up means move up and to the left, and all the semantics will be background. principle, there's no reason we can scale. Yeah.
Do you initialize this latent space?
It is a so in VQ you have this code book, right? So it's like 8 different codes, each with 32 dimensions, and then the magic is that you have an incoming variable that you find the nearest neighbor, and then you do a straight through gradient to the input, right? So you back propagate through that nearest neighbor locale. The actual initialization of them is like random, like normal, truncated to a small, small variance. But these codes are randomly initialized continuous codes that then are back propagated through with a straight through the nearest neighbor locale. So that's vector quantization.
So maybe like in Mamba paper, so they played with the initialization of the latent space, and that gave them a lot of the benefits. So maybe if you try to initialize it in a better way, then you can get them more expressive space.
Maybe so, yeah. We haven't played with this at all, so it may well work better. Yeah.
I was curious, in those examples, is it like human controlling the actions?
Yeah, I mean, these exact ones might have been just, we just developed the model in a collab with a particular action sequence. But for example, I think all of these were controlled by humans. These 4 different trajectories were made by people on our team just playing with the model. The inference time here is still needs to be improved, so it's about 1 second per frame at the current rate. Obviously, we need to get that to 30 or 60 to be like actually playable. But yeah, these are data generated by us. Every month or so, we have a challenge where we upload an image with a particular goal, and everyone tries to play it to like beat the game for this simulated analysis.
So just to continue on that, if you said there are 8 actions, what do they map to? Like
Yeah.
8 directions of movement?
That is a great question. I would love if we had an illustrative example of that. But in these platformers, you can imagine that the cardinal directions are very present in the data. We tend to find that at least 4 of them map to those. There tends to be like a jump up to the left and up to the right, as well as like chaos buttons. So like, if you're playing like Spelunky, like occasionally you'll set off a trap and a bomb will explode. Usually in these games, or in Hollow Knight, like you attack something and there's a big flash of light. Usually when we step the model like this, at least one of the buttons will be some kind of explosion. So yeah, it's like if you imagine just like a factorization of the future into like the k-means or whatever of the different things that can happen. That's what we get. And of course the indices are completely ungrounded here. So there's no way without actually playing with it, knowing how to control it. But that's why we tend to interact with it by just seeing all the different features and picking from. That said, I think I have some behavior cloning results here that show like you can very rapidly adapt to that like pseudo ungrounded action space. So in practice, I think it'd be fine. So there's just a couple things that we observe here, like parallax scrolling is a very common feature in 2D platformers. The foreground moves faster than the background, and we see this repeatedly. It's a reliable effect across like a lot of different input prompts that you can cause. The model kind of implicitly, right? We don't label any of this, just implicitly picks up the fact that like certain things are obviously foreground, other things are obviously background. Robots. Okay, so we're very happy with how well it controls robots. So basically, the consistency is a little harder to the point about like 2D platformers and action space there. Like the consistency on this action space is a little harder to probe. But basically, we tend to get actions that look a little bit like, moving the arm toward the object, pulling it away from the object, right? And in this case, where the arm is like on the floor, you still observe similar behavior. It's just that it's like the semantics are a little different. But basically, the visual quality we're very, very happy with in robotics. And I think that we're evaluating on some 3D stuff now. I think there's no reason to think that it won't work well. Maybe it needs more scale. Maybe it needs more expressive action space. But that's basically it. behavior cloning. So basically, if you have learned an action space from videos, if anyone's familiar with neural probabilistic motor primitives, NPMP, it's like you've learned like a latent control space that kind of describes what the underlying control factors are that generate a video. And that means that you can learn a behavior cloning policy in this space from watching YouTube videos. So like, as long as your videos show the kind of domain you're interested in, let's say like playing 2D platformers, then it should be reasonably easy to learn a policy in that arbitrary latent space. And then we find that we can very rapidly map that policy that's learned to the real actions of the real environment with very few interaction steps. So in practice, the number of steps down here, we've labeled it expert samples. This is like how many real actual interactions with the environment do you get to see before we start evaluating you? And the purpose of those real actual environment interactions is to learn to map the latent space to the real space. And like, I don't know, it's like 100, 200, maybe 300 steps, and this is not episodes, right? It's just individual time steps, which in the case of these like ProcGen environments is often like far less than the length of an episode. Already you can achieve like basically expert performance at some of these groups. So it basically, you can learn an awful lot from completely unlabeled control data, and then very rapidly with your learned latent space adapted to the real task you care about. So applying this to something like robotics seems like definitely so. Yeah, so scaling plots, it's the same scaling behavior that you see with all transformers. Looks like we can continue to add more data and compute, and things will continue to get better. So yeah, in terms of like what you can actually do with this, like on your own laptop, we find that CoinRun, one of the ProcGen environments, is actually very easy to model with a relatively small gene model. So from the paper, there should be enough information for you to reproduce these kinds of results. And we say a single TPU, but it could be a GPU on your desktop. And this is where we started our own research into this approach. And so we're very confident that you could do this too if you're interested. Basically, train a small tokenizer, train a small dynamics model with masskit on completely random behavior that you collected with a random policy. And you tend to get outputs like this. So like they're not all perfect. You see this this one like near the middle there with the black screen, he's like drilling into the wall, right? So you get some hallucinations in terms of the behavior, but in terms of the actual kind of like local consistency of the dynamics, they seem pretty good to me, and this is achievable with very limited kind of resources and on a standard benchmark. Yeah, so we kind of view this as a very early step toward being able to generate interactive environments, perhaps for agents, perhaps for humans, going forward. And like I said about the step time, like you don't want your environment to take 1 second per step, but it's just a matter of time until these things improve. Better distillation, better hardware, other improvements that allow us to like reduce the model size. So I think there's a very real future for like fully generative game engines, effectively, that are learned from passive data that don't cost anything to create because someone else has created them. The only costs are training the model on the data that's all. So yeah, anyway, that's the majority of it. But if yeah, let me know what do you think if you have any questions.